Zermelo-Fraenkel set theory and the axiom of extensionality, the problem of abstraction and equality. This video is meant to be proof the axiom of extensionality is absolutely false, but also relatively true. Because it can be relatively true is why it is so hard to prove that it is absolutely false. Here is the axiom of extensionality as presented by Wikipedia, which I understand Wikipedia, not the best reference, but in this case it's completely suitable. There is a couple important takeaways from the definition of the axiom of extensionality. The first is, given any set A and any set B, if for every set X, X is a member of A, if and only if X is a member of B, then A is equal to B. The converse of this axiom follows from the substitution property of equality. And the interpretation is the really important part here. And essentially what this is saying is that a set is determined uniquely by its members. And only by its members. Okay? So this is where things will begin to break down later in the video. Okay, so before I go into discussing what the problem is, I want to first cover the idea of set and element, because it's actually not a single idea. Each one has two different states they can kind of exist in. There is a set and element as they exist in concept, and then there is a set and element as they exist in application. And while the two things are similar, they're not exactly the same thing. Okay? In concept, a set is a set. It's one set. And a set is a thing, one thing. And a set may contain elements. That's all that determines what a set is in concept. Okay? This means that, given the rules of set theory, and particularly the axiom of extensionality, the conceptual set, any conceptual set, is a conceptual set. And so they're all identical. And it's because sets in concept don't have elements. They don't have any defining quality or value or anything else. Okay? And so the set is referring to an idea, the idea being the idea of a set. So if we said we had 10 conceptual sets, okay, those 10 conceptual sets are all referring to the same singular one thing, the idea of a set. So those 10 conceptual sets are all equal or equivalent or identical. All right? However, in application, a set is determined by its elements. Okay? So now we need to look at elements. An element is an element, it's one element. And this is in the conceptual. Okay? In concept, an element is one element, and that's it. Okay? An element is a thing. One thing. This is all that determines what an element is in concept. Okay? And now this should already make a noticeable issue. A set and an element are only required to be things. Okay? So in theory, that which is an element may also be a set, or that which is a set may also be an element. These two separate concepts can be applied to one thing. All right? And we call this a subset, or, we use other terms for that. But a element can be a set, and a set can be an element. Okay? Even in the conceptual, there's no real difference here between what they are, unless you consider that a set may contain elements. But there's no restriction on an element containing other elements in the definition of an element either. So while it's not explicit, it does not explicitly forbid it either. All right? And so now the important thing is what an element gains in actual application. In actual application, an element, or rather, what the idea of an element is referring to, is quantified. All right? It gets some sort of value of some sort by some means. All right? And so this is going to bring us to what determines the equality of a set and element. All right? So for two sets to be equal, there must be two sets, and both sets must contain the same number of elements. Now this can be zero, they can both contain zero, and then they're both empty sets, and thus they're both the idea of an empty set. If they contain a number of elements, though, each set must contain exactly and only the same elements as the other set, such that any given element from one set must have a single and only a single matching or identical element in the other set. Okay? To determine the equality of two elements, we have to consider the quantification of an element and the quantification of another element, and that those two quantifications are equal. That's what determines the equality of a set. They're quantifications. Or, I'm sorry, an element. That's what determines the equality of an element, is their quantifications. So what we are saying is our two sets are equal if they contain the same number of elements and the quantification of the elements in one set matches exactly, in terms of value only, the quantification of the elements in another set. Okay, so what we're saying is that the equality or equivalence of two sets is determined by its items, and that the equality or equivalence of the count of items in each set, as well as the equality or equivalence of the quantification of each item in each set, has a matching pair in each set, then the two sets are equivalent. Okay? And so the core idea here that we need to look at is equivalence and equality. And I think we all generally understand what equivalence and equality are, but I also think that's part of the problem. We think we understand what they are. And so I have to quickly illustrate this. When we say two things are equivalent or equal, what we're saying is something equals something, or something is something. 1 equals 1, 1 is 1. And this is probably the simplest example. It's what we learned in kindergarten and elementary school. Okay, what is on the left-hand side is what is on the right-hand side. Okay, or what's on the right-hand side is on the left-hand side. The two things are the same thing. And that is what equivalence and equality are about. Is this the same thing? Okay? Is what's on the left what's on the right? And to extend this a little bit, we can look at x equals y. Okay? This more clearly illustrates what's actually going on than using actual numbers. Because here, we can see this is actually problematic. All right? Are we asking a question, and are we making a statement? If we're making a statement, there's no problem. We are saying x and y are equal. For some purpose, whatever that purpose is, we are stating that these two things are equal. The problem comes in with the question. Is x equal to y? And the answer to that depends on circumstances. Are we speaking specifically of the symbols x and y? Are we being literal here? Is what's on the left what's on the right? Well, no. These two things are not equal. But again, that's not exactly what we're talking about, okay? Or it might not be, because it's circumstantial. Maybe we are talking about the symbols, but in most cases, we're not talking about the actual symbols themselves. We're talking about something like this, where we have x and y, and we're saying, or we're asking, is x equal to y, okay? Or we can be asking or making a statement at the bottom. Either one is correct at this point, because we have made the statement that x equals 1, and y equals 1, therefore x does equal y. So you can make the statement, and the statement is considered true, or you can ask the question, and the answer is yes, they are equal. And so this makes it a little bit clear that when we say two things are equal or equivalent, we're not talking about the abstractions that we use to represent those things. We're talking about the identity of the thing itself, okay? We are talking about the idea that the abstractions themselves represent, okay? So we're not saying, is X Y, okay? Because X is not Y. What we're saying is, what X represent equal what Y represents, all right? And so, again, this seems incredibly simple and unproblematic. So now, let's look at some examples from the axiom of extensionality. And all of these statements were made under the assumption that the axiom of extensionality is true, okay? And if we look at each one of these examples, there's some statements made about each one, and that these statements are true. So if we look at example 1, we have 5 sets, A, B, C, D, and E, okay? And A, B, C, D, and E all have the same elements as part of their set. They have the numbers 1, 2, and 3, all right? So, given the axiom of extensionality, the following statement is true. A equals B equals C equals D equals E, all right? And by the rules, that is correct. Those statements are equivalent. They are equal. They are referring to the idea of a set that contains the elements 1, 2, and 3. So now we have example 2. We have 5 more sets, F, G, H, I, and J. And each one of these sets contains square, circle, and triangle. All right, so given that all the sets contain the same 3 elements, the following statement is true. F equals G equals H equals I equals J. Again, according to the axiom, this is true. They all contain the same elements, therefore they are the same set. Now example 3 is K, L, M, N, and O. Here they have red, green, and blue, except for O. O has blue, yellow, and green. So now, given the axiom of extensionality, we can say the following statements are true. K equals L equals M equals N. That's a true statement, or conglomeration of statements. K does not equal O. L does not equal O. M does not equal O. And N does not equal O, though. And this is because O contains the element yellow as opposed to the element red, like the other 4 sets. So the axiom of extensionality says that the first 4 sets, K, L, M, N, are the same set, and O is a different set. And now given the 4th example is, given the sets from the other examples, we can say the following statements are true. A does not equal F, and F does not equal K. Therefore, A does not equal F does not equal K. B does not equal G. G does not equal L. Therefore, B does not equal G does not equal L. Okay, and we can do this with each one of the individual sets from example 1 and then picking the matching set from the other 3 examples. None of these sets from any example are, according to the axiom of extensionality, equivalent to any of the other sets from any of the other examples. Okay, so here's where I start to pretty clearly illustrate what the problem is. And again, I understand there's a rebuttal to be made here. and I will get to that. However, let's consider what's right in front of us. On the left, I have the 4 examples that I originally presented, where all of the statements were true. And on the right, I have an image. And in that image is 5 sets. And each one of those 5 sets has 3 labels. Okay? So now my first question is, does the presentation of this image, without me making any further statements, present a problem to the statements on the left? If you think it does, what? Because I haven't made any assertions about this image yet. Okay? There are conclusions you may have jumped to, but I have not asserted anything. So what exactly does this image present as a problem to those statements? At this point, nothing. Okay? They have similar labels, and there's 3 things in each, and they happen to share the same colors, but that's it. Except, I made the statements on the left based on this image. Those statements are statements about these sets in the image. Okay? And again, I understand the rebuttal. I completely get it. But let's go over this before we get to the rebuttal. Okay? So we have example 1. We have 5 sets A, B, C, D, and E. And we are saying those 5 sets are the same set because they contain the same elements. 1, 2, and 3. Okay? Well, if we look at the image and we find sets A, B, C, D, and E, we can look at those 2 sets and say without a question, those 5 sets, and say without a question, none of those sets are the same 5 set. Okay? About the only thing that can be said in terms of example 1 to make them be considered equivalent sets is they all contain an element that has a number 1, 2, or 3. And the same is true for example 2. The only thing that makes these 5 sets similar is that they contain squares, circles, and triangles. Okay? No mention of the size or anything else about the triangles, just they contain the triangles. And the same for example 3. The sets I'm presenting in those examples contain the colors from these sets represented over here, but that's it. Okay? Now example 4 is really interesting because we're saying A does not equal F, F does not equal K, and A does not equal F does not equal K. But if we actually look at the image, A, F, and K are equivalent. They are equal. Okay? It is the same set. And that's the point of a statement of equality. Okay, right? Because this is what it's about. Is saying that 2 sets are the same set. Not that the representation of the sets are equal, but that what those representations are representing are one and the same. All right? And so now, the question again. When I presented this image, what changed? Well, the circumstances changed. Okay? You assumed that the identity presented in the original examples was an absolute identity. So if we say example 1, set A, the presumption was that 1, 2, and 3 were the identities of the elements. Okay? But they're not. They're not at all. If we look at the actual elements, a thing is what the thing is, without qualification, quantification, abstraction, or anything else. What something is exactly what it is. And if you change that, it is no longer the same thing. It is not identical. It is not equal. It is similar. Okay? So the only thing that actually changed here was the circumstances. And this means that we have two different circumstances to consider. Do we consider the circumstance where we were unaware of the image? Or do we consider the circumstance where we were aware of the image? Okay? And if we are talking about equality of what something is, then it is with the image that matters, not without. Okay? And this is the problem. This is precisely the problem, though it's hard to put into one sentence. It is about presumption of circumstances. Okay? So, presumption of circumstances is precisely the problem. Okay? And this is what ties into what I believe is the main rebuttal that would be made. And it's that you have to supply absolute circumstances to the axiom of extensionality. But that's the problem. It's a presumption. And it's a false presumption. Okay? Because you can only provide what appears to be absolute circumstances to the axiom of extensionality. Okay? When I made the statements on the left, everything appeared to be the absolute identity of what we were talking about. And if I had never presented this image, there would be nothing to say otherwise. Those statements would be true. Upon presentation of the image, though, they are clearly, without question, false. Okay? Because the absolute identity is not what was presented in the examples. It was just assumed it was. All right? And so this makes the axiom of extensionality circumstantial. And we get that to some extent, and this is where, again, where the rebuttal comes in. We try to use that as a weapon when these type of problems are presented. Because the response will be something along the lines of, I switched the context, or the subject that we were talking about, or that I went out of my way to craft statements which would appear to be true, knowing they're not, and knowing I was going to present that information later. But my intent doesn't have anything to do with this problem. I wouldn't have been able to prove this. I wouldn't have been able to carry out my intent if this problem were not already present. Okay? And to think about that another way, or kind of in the same way as I just said, what if I had never presented this image? Okay? Now, this is a specific example, but this particular idea happens constantly. Okay? We presume we know the absolute identity of something, or that we're presenting it in a manner that is absolute relative to the context, to the circumstances that we're talking about. But we don't actually know that's the case. And so, again, this makes the axiom of extensionality circumstantially true. But if we say the circumstance is absolute, such that we are actually talking about what the axiom intends, the intent, which is to determine if two representations of something are actually referring to the same something. Okay? So we can't use context as a weapon against proof of the problem. All right? Because the axiom itself is intending to speak in the absolute context. That is its intent. And its intent is that we supply absolute identity. And if we do supply absolute identity, then the results from the axiom are true or are false, absolutely. Okay, such as it's absolutely true or it's absolutely false. But if we supply improper circumstances, whether we're aware of it or not, to the axiom, it can produce results which appear true, but may later be provably false. So this allows the axiom, because there's a condition, okay? If the elements in each set are equal, and there's the same amount of elements, and only the same elements in both sets, okay, then we're saying the sets are equal. So condition, and then a statement of equality based on that condition. And the rule for that condition is what allows us to supply non-absolute identities. And it's not its fault, but it does allow it, even though it intends for us to provide absolute identities. The problem of the axiom of extensionality is the presumption of circumstances. The axiom of extensionality is absolutely false, but may be relatively true. And an understanding of these two things is part of the problem, and I'll cover this in a minute. The truth of the result produced by the axiom of extensionality is circumstantial. Because the truth of the axiom is circumstantial, it can produce results which are contradictory, such that it can say something is true when it is not true. The axiom of extensionality is circumstantial because of a difference between the intent of the rules of the input to the condition of the axiom and what the input to the condition are in actuality. This difference between the intent of the rules for the input to the condition and what the input actually is results from a presumption about equality and how that relates to the input. This presumption creates the possibility for something which is not absolutely true to appear to be absolutely true, which causes the condition of the axiom to be met and appear absolutely true. Again, absolutely true is the important part here, and I'm going to get to that. Since the condition for the axiom is met, the assertion of equality takes place. However, the assertion of equality is based on the presumption that the result of the condition was absolutely true. The presumption of absolute truth from the condition causes the assertion of equality between sets to potentially be false or contradictory, such that it will say two sets are equal when they are not. Okay, I think an important thing to cover real quick is absolute and relative truths. To prove something true, you must prove it is always true. To prove something false, you must only prove it false once. Something which is absolutely true, is always true, and is only true. Something which is absolutely false is anything which is not absolutely true. If something can be true, but may also be false, then it is not always and only true. Thus it is not absolutely true, but absolutely false. If something can be true, but may also be false, it can be said that it is relatively true or relatively false. If something is always considered within the same circumstance, it may appear absolutely true, but that does not mean it is absolutely true. And I think these things are important to remember, because a lot of times we think we're talking in terms of absolute true and false, absolute truths, but we're speaking in relative truths. And a lot of times we realize this, but where it becomes a problem is when we don't realize this. And that's what I'm getting at here, and that's what those examples in that image illustrated. is when you don't know that you're wrong. Okay? When you don't know that circumstances are at play, or don't recognize those circumstances and the full implications of them. And the reason I think it's really important to understand these is there's some implications in here that I don't think we understand. Okay, if something is relatively true or relatively false, we may think that inherently makes it absolutely false. Okay, because of the previous statements. If something can be, okay, but just because something is relatively true doesn't mean it can also be relatively false. If the circumstances were constructed in such a manner, something which is relatively true could also be absolutely true. And worse yet, something which is relatively false can be absolutely true. And that's what really messes everything up, okay? Because if it's false, okay, that is not absolutely and only and always true, okay? But you have to realize that statement of false, that identity of false, is circumstantial itself, okay? Just like the identity of true is circumstantial. Just because it is circumstantially true doesn't mean it is absolutely true. And just because it is circumstantially false does not mean it is absolutely false, and it does not mean that it cannot be absolutely true. And the problem here is really the binary way of thinking about things in terms of true and false. So we're going to come back to this absolute and relative truths in a minute here. But we kind of have to jump topics again. And I know it bounces around a lot and it seems a little disconnected, but it does come together in the end. So let's bounce back to equivalence and equality, because that was what was actually causing our problem in terms of circumstances of the input. We were presuming two elements were the same, and worse yet, we were actually presuming certain elements were potentially different elements when they were one element, but we'll get back to that. For now, we were presuming two elements were the same element, and that was part of this condition that makes this statement. Okay, so this is what we think we're saying with equivalence and equality. Okay, this is the intent of it. We have abstractions, and the abstractions are referring to an identity. And now we realize even here this is kind of wrong, because one is on there twice. It's not an identity itself, it's an abstraction of the idea of one. So, but we get what's going on here. The intent of an equivalence and equality statement or question is one of what something is, okay, what it actually is. And we use symbols of some sort, whether it's spoken, written, actual symbols like X and Y that are written, or one. We use the symbols to refer to these things that are. And then we're asking if these symbols are referring to the same thing. So this is what we think we're asking when we do this. Okay, this is me interjecting and editing real quick. I realize that my use of the number 1 here might create some questions or some associations or confusion that I didn't intend. I was just previously using 1 and continued on with that. I've been trying to avoid using numbers because numbers actually have this same problem, and they help hide this problem inside of the axiom. So when I'm saying 1 here, what 1 actually is, that could be anything. That could be a circle, a ball, the moon, a planet, a ship, a cat, a dog, or something else. Okay, but the point is, you have to observe it first. So back to the regularly scheduled program. This is actually what happens. So there is what one actually is, whatever that is, okay? It is one as it exists, okay? We have to then observe one, the idea of, can't even say idea yet, we have to observe one, whatever that is, all right? And from that observation, we will form the idea of one, all right? And the idea is not necessarily observation, and the observation is definitely not what one actually is, okay? It's the quantification of one. It is the first reference to one. And then we have these other references building up. So we have now an idea of one, and from that we form an abstraction or representation of the idea of one. And that's actually what we're using in these equations. So when we say one is the identity, this is the chain of events that actually has to happen. All right? And then we realize x, y are also abstractions. So this is also happening for them. And what is actually going on here, this is a high level view. So let's look at it another way. There is what one actually is, okay? And then there's the observation of one. And we can say this is the function O1. And we're going to assign it to OID. Then there's the idea of one. And we'll call this the function I, and we're going to use the variable OID in it. And we're going to assign this to IID. And now we need to make an abstraction of that to use in these equations. And we're going to call that function R, and we're going to use the variable LID. Or I'm sorry, IID for we got from the previous function. And this is what we're going to assign to RID, and we're going to use RID in these equations. And in this case, it's 1. All right? And if we look on the left-hand side, it's just represented as letter equals alphabet position. You know, just an extreme simplification of what's actually going on there. Okay, so we have what a statement of equivalence or equality is actually saying here, okay? It's saying there are things, and we are going to abstract what that thing is, potentially, an abstraction of an abstraction of an abstraction, and then compare those abstractions. And this seems a little silly to me. Now, don't get me wrong. I understand the importance of it. But it seems potentially silly. Because, again, these are oversimplifications of what's going on here. All right? But there's a lot of presumptions taking place. And really, I don't think you're asking a comparison between identities. At least not in most circumstances. And you're certainly, in most circumstances, not comparing absolute identities. And we can see that a little more clearly when we break it down. I mean, okay, so we have a function which returns to a variable when the variable is used in another function, which is then returns to a variable which is used in another function, which returns a variable that we use to represent something. Okay? So we can just say we have fx and gn. Okay? We have two functions, and each function gets a variable, and we're asking, is the outcome the same? And it seems that, to me, regardless of what x and n actually are, the answer to that question is who wrote the functions? Who writes function f and who writes function g? Do I get to write both of them? If I get to write both of them, then is there some other constraint? Is there some rule that I don't get to make these two things equal? Who decides that rule?
Okay? If it's just me, I can decide whatever I want. Okay? As long as I agree upon it. If I don't want this to be true, it doesn't have to be. If I do want it to be true, it can. All right? And so really, the variables themselves are irrelevant. The input is irrelevant if the abstraction, if the function is completely arbitrary, if I get to decide in all cases. All right? So it's really just, does function equal function? Does the result equal the result? And the answer to that is just depends on how similar or different each function is and in what way they're different. There's no real statement being made here about the input or the identity of the input actually going on. It's not to say there can't be, because you can construct circumstances which are true, which do make it have some meaning, but fundamentally, like, there's no requirement there. There's absolutely no requirement. It's who gets to write each side and who gets to decide the constraints, and do all parties agree? And that seems really problematic. And the reason I think it's like this is because there's a pre-assumption even here that we don't realize, because it's the same pre-assumption over and over again. And that is the presumption of identity. We are assuming at the top of this what one actually is. Okay? There is a presumption from the observation that thing is that it is in fact even one thing. Okay? It could be that the observation is not absolute of what it is. And therefore there's some quality or essence lost. And if that's the case, then you could potentially see the same thing in two different circumstances and think that it's two different things, not the same thing. Okay, so I feel like the idea that fx equals gn is a little arbitrary, and so I need to give it a real example behind it. Okay, and so we have this image here, and I'm the one who constructed this image. I am the absolute arbiter of truth in regards to this image. And you as a listener are going to be aware of the absolute truth of the image. And we're going to have two observers, observer F and observer G. All right? So the absolute truth of the image is, there are not 7 examples here. There is one example. And it looks like example 7. Okay? It is one thing with parts inside of it, and the parts have properties, and the parts have space in between them. All right? Now, the other 6 are restricted observations of that thing. Okay? So now, if we presume that if observer F and observer G cannot have the same method of observation, at least not initially. Let's say they cannot both observe the same example. If they make an observation and they compare their observation, how right or wrong is their observation individually, but also then when in comparison to one another, such that they're trying to make a statement of identity, they're trying to make it say these two things are equal, how wrong is that answer? Well, they would say that it's not equal. They're looking at different things, okay? Clearly that's false. We've already stated that is false. But because they cannot observe certain aspects of what it is, they're wrong, okay? They're wrong in their individual observation because the properties of it that they have to go off of are not complete, but then they're wrong in their comparison because of it. All right. So now let's say there's 7 observers. Okay, observer 1 through 7, and each example is what they're observing. Okay, so what if observer 4 can communicate with observer 3, and observer 3 can teach observer 4 to see green? Okay. Now, what if observer 4 and observer 5 talk, and observer 4 teaches observer 5 how to see that shade of red? And observer 1 and observer 2 talk, and observer 1 can now see the separation of things there. Okay? And then 3 talks to 2 and shows them color, and 3 talks to 1 and shows them color. Now, 1 through 5 are all seeing the exact same thing. How right or wrong are their individual observations in regards to the absolute truth of what something is, what number 7 is, versus what they observed? And then how accurate is their comparison that they're observing the same thing? Okay? Well, if we're just talking to the first 5, they are all in agreement. They're seeing the same thing now. And that's a true statement. They're wrong in their observation, but they have made a true statement. All right? But now, what if we include observer 6? Okay? He gets everything observers 1 through 5 gets, but he's like, no, there's space right here. These aren't actually one thing. These are individual things. You just don't see the space in between them. Do they now all agree that they're looking at the same thing? Well, no. They don't agree. It's clearly at least 2 different things. Okay, that's a false statement again. And now, what if we include number 7? Okay? He's going to be in disagreement. And suddenly we have 3 things. All right? But now what if 6 can teach 5 how to see the space? Well, now 2 people agree, and 4 people agree, and then there's 1 person by themselves. And at this point, it becomes a matter of who teaches who what, and who do you decide is absolutely finally right. Now, you could conclude maybe they get to number 7. All 1 through 7 are finally in agreement that it's 7, right? Is that true? Well, we said it was true in the beginning, right? So it must be true. But let's change it. It's not true. It's a black square in the background. It's just rotated. The whole process starts over. Where does it stop? If somebody who is making the decisions here about what is true or false is not the person or the thing, it is not the actual arbiter of truth making that assertion, then there's no end to how often this cycle can repeat. And that is extremely problematic. Absolutely problematic. And so that is what I'm saying when it's F and G. Because first off, it's just dependent on what they can observe in the first place. And then, when we take it farther in there, their observation isn't the sole determiner. What do they know? What do they call things? What other information is being built in there with those abstractions? Because an abstraction isn't necessarily just lossless. Okay, you don't necessarily just lose qualities when you start abstracting. You can abstract inequalities as well. If somebody who's making the decisions here isn't the actual arbiter of truth, or if there is no truth, There is no end to this. Okay? And what do I mean when I say there is no truth? Consider the question we see all the time of two people arguing over if a number is a 6 or a 9. And people are often like, well, no, there's a context. Somebody drew a 6 or a 9, and that's what they meant. That is the solution to that problem, right? What if that's not the case? What if a bunch of birds flew overhead and they all took a dump and it just so happened to land and look kind of like a 6 or kind of like a 9? Is it a 6 or a 9 then? Is it? Who decides? Do the birds need to come back and tell us if they actively were trying to do that in the shape of a 6 or a 9? That seems a little absurd. And so this is really what it's saying. This is what the axiom of extensionality is doing. Okay? It's not a question of if it's doing it. It is absolutely doing this. And again, it's not the axiom of extensionality's fault that it's doing this. It's actually equality doing this. The requirement or the statement of equality between the elements. But because the axiom includes that, this is what the axiom is doing. Okay, so I want to briefly cover what I think the rebuttals would be to this, all right? And I think they're all going to fall into the category where the idea is that context is key in some manner. And I completely agree. Context is key. Context is key to solving the problem. And the reason that context is key to solving the problem is because the problem is context. Okay? So you can't exactly say you're going to solve the problem by using the problem. At least not exactly. All right? So you might say that I switched the context or subject of the examples that I gave. And that's not exactly true. The context, the subject of the examples was always the image, the sets in the image. All right? What changed was your ability to observe the identity of those sets. All right? And it changed because at that point I was actually in control of it. I got to decide the way you resolve those. All right? And it's not a problem that I did that. Okay? That's not that you can't say that it invalidates this problem. Because that is precisely the problem. The circumstantial nature of the observations and the assumption that the input being put in is absolute. Okay? And so you could maybe say I did improper notation. But you can only say that once the truth of the problem has been observed. And when it is so obvious like this, that's when we're like, oh, context. Context is the problem. Context is the key. And yes, I made an example where it is obvious. But because that's the only way that you can show the problem actually exists. If the problem didn't exist, I wouldn't have been able to do any of this. Okay? And if the problem exists, but we don't know it exists, how can we point it out? And so the only way to do this is to craft an example in this fashion. Okay? To craft an example where you can assert the statements are true, and then later on, bring out the actual identity of the thing and show it. Not make a statement about it, because that's important too. Showing could be considered a statement, but I'm talking about statements of abstraction, written, spoken, something like that. I didn't make that kind of statement. I showed you the identity of the sets, which removed layers of abstraction that took place when I made the statements about it. Okay? So it's not a valid thing to say is a reason this isn't a problem. You're able to say these things because the problem exists and we can use the problem to fight it, but it doesn't invalidate the problem in the first place. And the other thing I think you could say is that the axiom wants or requires absolute context an absolute identity, okay? But you can't actually enforce that, all right? We've already shown that any input you give is circumstantial, okay? It is relative. It is inherently not absolute, okay? And if that's the case, if you're saying this is a requirement of the axiom, then the axiom is unusable because you can't provide the input that it requires. And so then it's still false because you can't even use it. All right? And I think another thing you might say is, well, this is a problem for everything, so it's not a problem. Well, I would definitely agree. What I've outlined here in terms of equality is problematic for lots of things. But specifically as it relates to this, it doesn't change anything that it's problematic. You can't just ignore it because it's problematic. It's not how problems work. You can't just say, oh, well, it's a problem, and it's always a problem, so we're just going to ignore it. That doesn't work, okay? And the final thing I think somebody could say is, insert other axiom accounts for this problem. So some other axiom in terms of set theory and stuff will account for this problem. So it's not a problem. Well, again, that's not how problems work, and that's not how considering things in regards to true and false work, okay? If another axiom accounts for this problem, that's great. But first, you're switching the context, okay? You're moving the goalposts because we're talking specifically about the axiom of extensionality, and that other axiom is not included in here, okay? So in terms of just the axiom of extensionality, without altering the context to bring in another axiom, the axiom of extensionality is false, okay? And if we're saying it is false, if we can take some other axiom and combine it with this, and together they appear true, that still doesn't change the fact that this axiom is false, okay? So I think those would be the primary rebuttals, and I really, and I could think of maybe some other ways to say them, but it's essentially the same thing. You're going to try to say something that has to do with the context, okay? And I'm going to say you can't say context is a solution when I'm saying it's the problem. And we can even go one step farther and let's say, okay, I concede to you, context is the solution. Well, if context is the solution, doesn't that again prove that the axiom is only contextually true? It is only relatively true? So doesn't even me conceding what might be the counter arguments actually prove the truth of what I'm trying to say? Okay, so at this point, I'm pretty sure I've met the requirements for proof by construction and proof by contradiction to show that the axiom of extensionality is absolutely false. If there's other counter arguments or questions, I would love to hear them. And I do think I have answers for them. I don't think you're going to come up with something that completely invalidates this. But if you do, I'm completely interested in hearing it. Okay? But more importantly, why does this matter? And can it be fixed? Okay? And because it seems like a weird thing to be saying, right? Because we know context matters. Okay, we know we're supposed to be applying the right context. But again, we don't always know what the right context is. And even if we think we do, it's still a pretty large presumption. Okay, and we've shown that this can wind up producing contradictions, things which will seem true but are false. And if the axiom existed in a vacuum, I wouldn't care. And I wouldn't have a problem with it because it was in a vacuum. There's no implications outside of itself. But that's not the case. It doesn't exist in the vacuum, and there are implications outside of just the axiom. Specifically because the problem isn't in the axiom itself. It's in the axiom because of something the axiom does, but it's not that the axiom was intending this, okay? It's actually because the axiom states the requirement and the method of comparison as equality, okay? And so the implications reach backwards out of the axiom, okay? It doesn't just reach forwards. It doesn't just have implications when you build on top of this axiom. It actually shows that the problem predates the axiom, okay? It comes into the axiom because it existed beforehand, and the axiom pulls it in. And I think it's important to realize the axiom is absolutely false, even if for the most part it doesn't change anything. It doesn't change the way we use set theory. And if anything, it shows set theory is wrong, but in an almost perfect way, because it does take what the problem is and it turns it around and tries to use it to counter itself, okay? But the problem with that is it's not always perfect, okay? It doesn't abstract itself out perfectly. Context doesn't abstract out context unless they're the exact same context. And knowing that's the fact is problematic. And so this is why I think acknowledging that the axiom is absolutely false is important. Because if you don't acknowledge that it is absolutely false, then you miss something, okay? You miss out on the steps that take place and the understanding of what the actual problem is. And if you don't understand the problem, you, one, probably can't come up with a solution to it because you don't recognize the problem. But even if you do somehow manage to come up with a solution, how do you know it's the solution? And how do you know what that solution means if you don't understand the problem? Okay? So it's important to recognize that the axiom is absolutely false, because this is showing us what there is actually an issue with our understanding of equality. And if we don't recognize the axiom as false, we're not going to investigate that. We're not going to go, well, hold on, this does kind of make sense, even if we don't like it, because I don't particularly like it. It's weird, okay? It's contradictory, and I don't like that because it's contradictory of almost basic logic. And we have to ask why, though. And I think that's really important, and I'm going to get into that more, because there's some things we left hanging, particularly around absolute and relative truths and what was actually going on with equality. But it wasn't important to go any farther with those to show that the problem exists. And so I'm going to make a follow-up video digging more into those. So then just the final question we have is can it be fixed? And the only way I see to actually fix it is to change the assertion that two sets are equal to being two sets are similar. Because there's not a way to fix the error in the condition. There's no way around it. Okay, we can say equality is supposed to be equality, but that's problematic. We can't actually provide absolute identities in absolute circumstances. And so I don't know how you would correct that condition. We're kind of stuck with the input being the way it is. And if the input is the way it is, then the only part we can change is the assertion that it makes, is that two sets are equal, but we'd have to change it to say two sets are similar. And I'm not sure the full impact that would have in terms of set theory. I'm just not sure. I'm not sure you can just, it's that simple. I feel like there would be rippling implications from that change. It changes the intent of that axiom, which is that the sets are referring to one individual set, one thing, one identity. And if you say it's similar, you're not saying that anymore. But at the same time, changing it does acknowledge the inherent problem to it. So yeah, I'm not sure it can be fixed. Okay, as one final thing, I want to come back to this example image real quick. Because I'm pretty sure I've shown the problem does exist. And I've given a few rough examples of the problem, but I haven't really explained the implications of the problem as it pertains specifically to set theory. I've more shown that the problem does exist in the axiom and how it exists or why it exists. But what is that actually? What does that cause to happen in terms of set theory? So if we look at this image, these are the sets from the examples as they actually are, okay? As opposed to the text representations I gave. And we can see here that sets are not entirely an abstract thing, okay? The implication from set theory is that a set is completely abstract, all right? It's only determined by its members. But now remember, I said that there should be a problem visible in that, because a set and an element, or a thing can be a set and an element, all right? And an element has some sort of value, but it's not determined necessarily by the elements it may or may not contain, because an element doesn't have to contain other elements, okay? It's unclear in how the quantification process happens of what an element represents, all right? And that's because, again, how that quantification happens is circumstantial to what you're talking about, or what is being observed, what the subject matter is, okay? If we're talking about numbers, well, then the quantification is going to be the idea of the number. We're going to see the numerals and stuff, okay? But if you're talking about shapes, well, it's more likely that you might try to draw the shapes in there, or you're going to talk about them in terms of area or something else. And so it doesn't specify what the quantification is, just that a quantification of what an element represents happens, okay? And this is good, because an element isn't always or isn't necessarily just the things it contains, okay? So if we look at our examples here, all of our shapes only contain a number, okay? But the shapes are colors, and they are of a certain size. There is a matter to their construction. There is a tangibility of some sort, okay, to their construction. The means of their existence has meaning to what they are. And leaving the quantification process of an element open-ended allows for you to try to fully quantify an element. Okay, again, it doesn't require it, doesn't specify it, because you can't actually guarantee you're doing that, but it allows you to do that. But the set completely ignores that, okay? As a set, the matter and means of its construction have no meaning in terms of set theory, in terms of the set and the element, okay? And so when you're saying two sets are equal and it's all about just the items they contain, then you're saying anything about the set itself is completely irrelevant. You know, if it has a shape or a size and that that have some meaning, okay? If there's a correlation of some sort between the set and the elements it contains, that's completely irrelevant in terms of set theory, okay? Unless you specifically take care of it in the quantification of an item. But the correlation between a set and an item, isn't necessarily something that's of the item or the element itself. If you were to quantify that element, there's nothing to say that that correlation would be part of that quantification. Okay, because that correlation could be of the set itself, or it could just be coincidental because of the set and the element. And so you lose any of that. That's all just completely gone in terms of set theory. And now, again, you can constantly shuffle your context around. Okay? That is the trick that it allows to let you keep accounting for this. Okay? Or at least trying to. But it doesn't account for the sustenance or the substance of the set. It just completely disregards it. And even insofar as the element, because it's not specific about how it has to be done, it opens you up to the possibility that it is done wrong. And in particular, something I want to specifically mention, then set theory, and not just set theory, but most concepts in math disregard, is the importance of order and space, or rather space and order in that space, okay? There is no meaning given to the space or construction of the set itself, okay? There is no assumption that maybe a set is composed of spaces for elements. For instance, if we look at example DIN, okay? That set has 3 spaces in it, and each space is for an element, okay? But those elements don't fill the space. There's a loss of the meaning of why is there separation inside the set itself? What is going on there? That meaning is lost in terms of set theory, okay? And same with EJO. And now you have the question of well, why is this the second element in the set in part of the set that's not like the other parts of the set? Okay, where's that meaning? That's not considered in any way, shape, or form, okay? Nor is, like, the circumstances in EJ&O with the numbers 2 and 3. They're technically larger in some manners than their container set. So is something being lost when we abstract them there? Or what is going on? What is the meaning there? Okay? And now there is no meaning. I intentionally just crafted some examples to illustrate these problems. I don't have a larger meaning behind it. But if you can think about it, you can understand why these things are problematic. And a counter argument to this might be, okay, well, the set actually contains elements that contain elements, and that would be a way of looking at it, but you're assuming you can identify this partitioning going on in the set. Or if you consider the set an element. Again, your quantification of it could be wrong. You're assuming you can identify this part. And this is why I think this part is important, is because this part has to do with space. We really do not give space the credit it deserves, okay? Because really, what it allows you to identify something, is it the something itself, or is it the absence of that something around itself, okay? What allows you to tell two things apart? Is it them themselves, or are you able to tell that they are two things because of the space? And we really ignore space a lot in terms of math. We add the concept back in later, but we immediately abstract it out
very first thing, pretty much in every concept we have going for us in math. And I think that is an issue. And I don't think we realize how big of an issue that is, because it doesn't matter until it matters.